centuries, we believed Roman concrete's durability was geological luck, or a lost secret formula. Today, we are demolishing that myth. The answer is not magic. It is a revolutionary chemical trigger hidden inside reactive lime clasts, tiny white mineral fragments that engineers previously dismissed as evidence of poor mixing. When a crack forms and water enters, those clasts dissolve, releasing calcium ions that recrystallize and seal the damage before it can propagate. The Romans did not stumble onto this by accident. They created it deliberately through a process called hot mixing, combining quicklime with volcanic ash at high temperature, generating a reactive matrix that no cold-mixed modern concrete can replicate. In this documentary, we decode the precise chemistry that makes Roman harbors outlast steel-reinforced bridges by 2,000 years, and show how that ancient formula is now being rebuilt in 21st century laboratories to solve the infrastructure crisis of the modern world. Our steel-reinforced bridges fail within decades. Roman harbor structures have survived 2,000
Analysis revealed a
years of wave
complex,
action,
interlocking
saltwater,
mineral structure
seismic
within the
stress,
ash
and they are
matrix,
still
a
getting
sophistication no
While
modern
modern
analysis
concrete
anticipated.
deteriorates through
Look at the
irreversible
visualization.
chemical degradation,
The self-healing
Roman
mechanism is
maritime
actively
concrete is
engaging.
actively
It
growing
works.
new
This
crystals
changes
in the
everything we
cracks
know
that
about
form within
Roman
it.
concrete
The
durability.
precise thermal mixing
Look at
process
that.
that makes
The
this
tobermorite
possible,
signature is
quicklime and
clear.
volcanic ash,
It's actually
combined at high
forming
temperature,
inside the crack.
generating
That's
a
how it
reactive
healed
lime
itself.
class matrix was not
Not
a lost
luck,
secret.
not
It
lost
was a deliberate
secrets.
engineering
Chemistry.
choice with chemical
Deliberate
consequences
chemistry
we only
encoded
fully
in a
understood in the
2,000-year-old
21st century.
construction
In
technique.
this
This
documentary,
confirms the
we
reaction
examine that
mechanism.
chemistry
The
in
material's
detail.
origin is
The
just as
specific
critical.
molecular trigger activated
Then we must
when
examine
water
the source
contacts
at
a
Campi
reactive
Flegrei.
lime clast. The crystallization process that seals structural cracks before they propagate, and the 2025 and 2026 laboratory breakthroughs that have successfully replicated the Roman formula with modern materials. Volcanic ash has outperformed our best technology. Here is exactly why. Scientists have finally isolated the microscopic mechanism that makes ancient concrete virtually indestructible. By analyzing the chemistry of lime clasts, the small white mineral fragments embedded throughout Roman concrete, researchers discovered a self-healing crystalline
Push.
growth system that activates the moment a crack
Together
forms.
now,
Water
move the
enters
stone.
crack. The lime clast dissolves.
Roman engineers
Calcium
used
ions
lighter
migrate
aggregates
into
at
the
the crown
fracture
to
and
reduce dead load
recrystallize as
buying.
tobermorite,
Structural
a
engineering
mineral that fills
intuition
the crack,
encoded in material
bonds to the
selection.
surrounding matrix, and restores structural integrity without any human intervention.
From this height,
This is not
the
history.
density of Roman
This is a
concrete
blueprint for
structures is
indestructible
astonishing.
infrastructure and the future of modern engineering. In this documentary, we trace the complete chemistry of Roman concrete from the volcanic geology of the Campi Flegrei to the harbor structures of Caesarea Maritima, from the hot mixing kilns of Roman construction sites to the 2026 laboratory synthesis of self-healing concrete derived from the Roman formula, and show how an ancient volcanic mixture
Roman
is now the
concrete
leading
self-heals
candidate
as lime
to
clasts
solve the
dissolve and
global
seal
infrastructure
cracks.
crisis.
Portland cement
The Ponte
self-destroys
de
when
Quattro
chloride
cavity
penetration
has
causes steel
spanned the
corrosion
Tiber
and
in
fracture.
Rome for 2,070 years. The concrete used in its construction has not been significantly repaired in the modern era. It does not need to be. Meanwhile, the reinforced concrete infrastructure of the 20th century is failing at a rate that represents one of the most significant engineering crises of the modern world. Bridges in the United States, Europe, and Asia. Built in the 1950s and 1960s, structures designed for 50-year service lives are approaching the end of their engineered capacity, simultaneously, at an estimated replacement cost in the trillions of dollars. The contrast is not subtle. Roman maritime concrete structures the harbor at Caesarea Maritima, built by Herod the Great.
This is a
under Roman
pozzolanic
engineering
ash,
supervision.
named
The
for this very
walls at
harbor,
Pozzuoli,
Pozzuoli.
the
The
breakwaters
Romans
at
unlocked
Cosa
its
have been
secrets.
submerged in highly corrosive saltwater for 2 millennia, and are measurably stronger than they were when they were built. Modern reinforced concrete placed in the marine environment begins to deteriorate within 20 to 30 years. The steel reinforcement corrodes, expands, and cracks the concrete from within. The concrete itself, once cracked, allows water and chloride ions to penetrate deeper, accelerating the corrosion in a feedback cycle that leads to structural failure. The conventional explanation for Roman concrete's durability attributed it to the unique properties of pozzolanic volcanic ash from the Campi Flegrei volcanic field, a material so strongly associated with hydraulic concrete that it gave its name to the entire class of pozzolanic cements still used today. This explanation was correct, but incomplete. It identified the ingredient without explaining the mechanism. Why does pozzolanic volcanic ash produce concrete that heals itself? Why does Roman concrete get stronger with age while Portland cement concrete gets weaker? The answer required not geological analysis, but chemical analysis at the molecular scale, and it was not fully available until 2023, when a research team at the University of California, Berkeley, published the results of X-ray microdiffraction analysis of Roman concrete samples from the harbor at Baiae. The mechanism they found was not what anyone expected. For decades, white mineral fragments scattered throughout Roman concrete samples were considered evidence of sloppy workmanship. Modern concrete production requires thorough mixing the complete hydration of all lime particles before the concrete is placed. The white inclusions, visible in cross-sections of Roman concrete, appeared to be incompletely hydrated lime clumps of quicklime.
While cold mixing leaves the fracture open, hot mixing allows the encapsulated reactive lime clasts to activate.
The Berkeley research team discovered they were the point. These lime clasts, white calcium carbonate, and calcium hydroxide inclusions, ranging from sub-millimeter to several centimeters in size, are
if
not
the lime
evidence of
clasts
poor mixing.
distribute
They are
evenly,
the
the
deliberate
modern
product
replication
of a
should
specific
hold.
mixing technique that Roman engineers used, and that modern concrete production has entirely abandoned: hot mixing. Modern concrete production uses slate.
The 10-week results are conclusive. The Portland cement shows significant surface erosion and crack propagation, while the Roman formula, after saltwater exposure, the Roman formula sample shows surface mineralization and sealed cracks, confirming the self-healing mechanism.
Allowing the violent exothermic reaction of quicklime hydration to occur within the fresh concrete mix. The temperatures generated by this hot mixing process, potentially exceeding 200 degrees Celsius at the point of reaction, created a chemical environment that cold mixing cannot replicate.
The morphology confirms the microstructure is consistent with the analog.
Elevated temperature.
This batch
producing
shows
a mineralogically
significantly high
distinct calcium silicate matrix with a porous, branching microstructure. Within that matrix, incompletely reacted lime fragments were encapsulated not as flaws, but as chemical reserves, stored energy, reactive capacity, waiting for a trigger. The trigger is water.
A comparison of CO2 emissions shows Portland cement at 0.9 tons per ton, while Roman formula
Calcium extraction for Roman formula concrete requires no high-temperature energy input, significantly reducing CO2 emissions compared to traditional cement.
Calcined clay is heated to only 800 degrees Celsius, far below the temperature needed for Portland cement, producing a reactive.
This batch of the Roman formula mix seems optimal. Monitor the tidal reach on section 3.
I agree.
And progressively
The strength results
the
are
process
promising.
is self-limiting. It continues as long as
This
water
specialized
and
mix,
reactive lime are both
mirroring the
present.
chemistry of ancient Caesarea Maritima, combines volcanic ash.
Roman formula concrete was specified for this exposed marine location, where conventional materials have failed within decades.
The tobermorite crystallization.
The specialized Roman formula concrete is pumped deep underwater, rapidly curing to form an impermeable
mineral growth reaction.
In the Netherlands, coastal defense is an existential engineering requirement. We are
calcium silicate hydrate.
The Harbor Project utilizes Roman formula concrete, the first time the material has been adopted outside Europe. The conditions that destroy conventional concrete within 15 to 20 years. The conditions in which Roman formula has already proven its performance for 2 millennia.
We're seeing excellent resistance to chloride ingress here.
And the self-healing properties are clearly demonstrated in this sample, exactly as predicted.
Close-up of the 3-year tropical test core, zero chloride penetration detectable, induced crack filled with tobermorite crystal, surface mineralization visible, the Roman formula performing in tropical conditions as predicted. The comparison is stark. This new section shows no wear at all. While the 30-year-old Portland cement is already deteriorating significantly.
The self-limiting nature of the process is as important as the healing itself. A repair process that continued indefinitely generating crystalline growth throughout the
deterioration
concrete matrix, rather than only
we're seeing significant displacement. It's past the limit for self-healing options. Look at the density of the tobermorite formation here. It's completely sealed the fissure.
Where water can penetrate, which means
the load-bearing capacity is sound.
Look at the density of the fill right here. It's almost completely sealed already.
Chemically stable. Cracked concrete.
Remarkable autonomous repair.
The healing response. By contrast,
Portland cement. 50-year replacement cycle. Continuous capital expenditure. Continuous carbon emission.
The volcanic landscape of Iceland offers vast deposits of pozzolanic material, strategically located near coastal infrastructure.
Global mapping shows volcanic distribution worldwide. The raw material for self-healing concrete is available across the planet.
Sulfate ions react with illuminate phases in the cement mix, producing
We need to
expansive
verify the
reaction
mix
products that
specifications
drive
against the
further
latest self-healing compound.
carbonation.
The surface life
reaction
projection
of
looks good.
atmospheric carbon dioxide with calcium hydroxide in the cement paste progressively reduces the pH of the concrete pour solution, removing the alkaline protection that passivates the steel reinforcement. Each of these processes is progressive and self-accelerating. The crack that allows water in leads to corrosion that produces more crack that allows more water in. Roman concrete, lacking steel reinforcement and built with a volcanic ash matrix that does not contain the
The
reactive
concrete
aluminate
above you
phases of
is
Portland
2,000
cement,
years old
is immune to
and has
all three
never been
deterioration
structurally
mechanisms.
repaired.
Its response
How did
to
they
cracking
build
is
this
not
magnificent
deterioration,
structure?
but repair.
And why
The
has it lasted
identification
so
of the hot
long?
mixing mechanism
That is what
and
we
the
must
tobermorite
uncover.
self-healing response in
Data developed.
2023 immediately
The data
raised
is
the question
clear.
that
Sea
material
level rise
scientists,
projections
structural
necessitate
engineers,
immediate
and
adoption
climate
of
researchers
advanced
have been
binders.
waiting to ask, can the Roman formula be replicated with modern materials at industrial scale with performance equivalent to or exceeding the ancient
It is
product?
done.
The answer,
The self-healing
emerging
concrete
from
is now
laboratory
the standard
programs at
for
Berkeley,
all marine
MIT,
construction projects.
and the Swiss Federal Institute of
Excellent.
Technology from
Roman formula concrete
2024
specified for the
and
subsea foundation
2025
structure, where maintenance
is
diving
yes
is
with important
impossible and replacement would require
The
decommissioning
volcanic
the
ash
entire
of the Campi
platform.
Flegrei has a specific mineralogical composition high in reactive silica and alumina, low in crystalline phases, that would reduce pozzolanic activity that is not universal. Not all volcanic
Replacing
ash
the near
produces
end-of-life
Roman-quality
marine concrete is essential.
Synthetic
The
pozzolans,
economic case for the
calcined
Roman
clays,
formula material.
industrial byproducts
The
such as
volcanic
fly ash and
geology
silica
that gave
fume
Rome
can
its
partially
empire,
substitute for
its
natural
infrastructure,
volcanic ash.
and its
But
legacy.
replicating the precise
Still
reactive
active.
matrix of the
Volcanic
original
ash
material
falling from a minor
requires
Campi
careful
Flegrei emission,
compositional control.
fine gray particles
The hot
settling on a
mixing
stone
process
surface,
itself
the same
presents
material
engineering
Roman engineers
challenges at
collected.
modern construction
2,000
scale.
years
The
of
exothermic
chemistry,
reactions of quicklime
one
hydration are
geological
hazardous
source,
in large volume applications
an infinite
and require
future
modified
application.
mixing equipment and safety protocols. The 2025 laboratory synthesis programs addressed both challenges, identifying synthetic pozzolan compositions that replicate the reactive silica-alumina chemistry of Campi Flegrei ash, and developing modified hot mixing
Scissors.
protocols suitable for large-scale concrete production. The carbon footprint
The most
implications
important
are significant.
engineering
Portland
in
cement
history.
production is responsible for approximately 8% of global CO2 emissions. The calcination of limestone to produce clinker releases 1 molecule of CO2 for every molecule of calcium oxide produced. A concrete system that substitutes volcanic ash or calcined clay
This
for the majority of
extraordinary
Portland
Roman
cement
concrete
clinker
structure,
reduces
built
the
in
embodied
100
carbon of the
AD,
material
remains
by 40 to
structurally
70%
intact and
per
is
unit
still
volume.
visited daily.
By 2026, Roman-inspired self-healing concrete formulations are being specified in coastal defense projects in the Netherlands, seawall
Modern
reconstruction
vault,
in Japan,
deterioration
and deep-sea
visible,
infrastructure installation
40 years
where
of
access
damage.
for conventional repair is impossible. The material that Herod's engineers poured into the
A
harbor at
side-by-side
Caesarea
comparison
2,000
reveals
years
the
ago
stark
is
truth.
being poured
The
again this time
1900-year-old
with the
Roman
chemistry
vault is
understood,
sound,
the
while the
mechanism
40-year-old
controlled, and the application delivered. The economic and environmental implications of self-healing concrete at global infrastructure scale are not incremental, they are transformational. The global infrastructure replacement cycle, driven by the simultaneous end of life of mid-20th century reinforced concrete construction, represents a capital expenditure challenge that no government budget can comfortably absorb. Bridges, tunnels, harbor structures, coastal defenses, water treatment facilities. The concrete infrastructure of the developed world was built in a concentrated period between 1,950
Crack forms, water enters, lime class contacts water, calcium dissolves, tobermorite nuclei, crystals grow.
Period between 2020, 2060. If self-healing Roman formula concrete can double the service life of infrastructure from 50 years to 100, or from 100 to 200, the savings in replacement capital are measured in tens
The
of
simulations
trillions of
confirm
dollars
the Roman
globally.
formula mix
The
meets the
environmental savings are
200-year
proportionally
specification.
larger.
Excellent.
Every infrastructure
Locking in the
replacement
design
cycle consumes
parameters.
energy,
Backing it up
produces
with
carbon
research.
emissions,
Utilizing the
generates
self-healing
waste,
concrete
and disrupts
means
the
we avoid
communities the
steel
infrastructure
reinforcement
serves.
entirely in the
Doubling
marine zone.
service life does not simply have these costs. It eliminates entire replacement cycles in the operating lifetime of cities and nations. The philosophical shift from
The first
build and
major
replace
bridge in the modern
to
era
build and
designed for a
maintain,
200-year
from
service
disposable
life,
infrastructure
utilizing
to
Roman
generational
formula
infrastructure,
self-healing
requires
concrete.
not just a change in material specification, but a change in how infrastructure is valued, financed, and governed. Roman concrete infrastructure was not maintained
The
on
carbon
replacement
reduction
cycles.
data is
It was
undeniable.
monitored and repaired
We must adopt this
opportunistically,
formula
the
globally.
self-healing chemistry,
But the economic
handling
projection-
the minor damage continuously. Human intervention, addressing the major damage when it occurred. 2,000 years of that approach produced harbor structures still standing in the Mediterranean. The volcanic ash deposits that made Roman concrete possible are not real. The Campi Flegrei field
Campi Flegrei, the Bay of Naples, the origin of everything.
Many of them proximate to the coastal and marine infrastructure that most needs a durable, self-healing material. The legacy of Roman concrete is not a historical curiosity. It is a geological resource, a chemical blueprint, and a demonstrated engineering performance record spanning 2 millennia waiting to be applied to the infrastructure crisis of the 21st century.